Hey guys, Chapter 11, STAT1800, Chi-square test. Let's get to it. Uh, kind of like some of the stuff we've been doing previously. The first time you see this, it's going to be little strange, extreme. Just stick with me. I think you'll find that chi-square test once we get a feel for them is a lot easier than two-way or I'm sorry, two sample test and even ANOVA. So guys, let's do it. So in this chapter, I'm going to teach you how to conduct a chi-square test for contingency tables and to compare two proportions. So contingency tables, pretty much what you need to think about from here on with chi-square test is chi-square test has its own distribution. If you remember, for example, a two-sample t-test used a t-distribution, and ANOVA used the f distribution, and chi-square uses the chi-square distribution. Even further, I want you to think when you hear chi-square, we are dealing with categorical variables. Let me repeat that. Huge. Tattoo this to the brain. When we talk about chi-square test, and we have chi-square test of independence, and we have chi-square goodness of fit test, we are dealing with categorical data. So contingency table example, if we want to examine the relationship between the dominant hand and gender, again, we have two categorical variables. Dominant hand is categorical because it's either left or right. Gender is categorical because it's either male or female. So we have two categories for each variable, so this is called a 2 by 2 table. And the illustration that they provide here is they examined a sample of 300 kids. Now, what they did, and we've looked at contingency tables earlier in the semester, it's been a long time ago, so maybe you don't remember. But anyway, they take the counts in the contingency table across hand preference and gender. So there were, of the 300 students, there were 12 that were female and left-handed. There were 108 that were female that were right-handed, and so on and so forth. Now, the chi-square test for difference of proportions, two proportions, starts out instead of, it kind of reminds you of a two-sample mean test where our null was mu1 equal mu2. The guys here we're dealing with the proportion, which deals with the count. Actually, it's a count out of a whole. Remember that whole x over n thing that we've talked about ad nauseum. So we make minor modifications to the minor but important modifications to the hypotheses. So the null hypotheses would be that the proportion of females who are left-handed is equal to the proportion of males who are left-handed, and the alternative is the two proportions are not the same. The chi-square test statistic, I don't think there's any way that I can sit here and use that as a demonstration and really speak it through, provide a narrative, if you will, where that's going to make any sense to you. Once we get out of this video and into the next video, where we actually start looking at numbers and how we, how we create these frequency observed counts and expected cell counts, then I think that'll become clear. So anyway, that's just a big old fancy schmancy test statistic formula for the chi-square test statistic. Now, something that is very important. Now at the bottom, it's assumed, and again, I'll teach you in fine detail how to come up with these expected cell counts, these expected frequencies. But keep in mind that our test statistic and ultimately our p-value isn't stable if our expected cell counts, each expected cell count, isn't at least 5. So it has to be 5 or larger. So our decision rule, now you'll notice that the chi-square distribution, which you're looking at on the graph there, it kind of reminds you a little bit of the F distribution. Big difference, the F distribution has 2 degrees of freedom. For the ANOVA model, it has the degrees of freedom for the numerator and the degrees of freedom for the denominator. The chi-square statistic just has 1 degree of freedom. Now I'll show you how to calculate the degrees of freedom. It turns out they're very, very easy. But guys, the decision rule and the way we make decisions, and decisions are either we reject the null or we don't reject the null, we fail to reject the null, is still the same. We embed all of our rejection region in the right-hand tail. So for example, if we're testing at alpha 0.05, then all of that 0.05 goes in the right tail. If we're testing alpha 0.10, then all of that 0.10 region goes in the right tail, which is the reject area. So these problems remind you a little bit of the F distribution, but fundamentally they're completely different. So computing the overall proportion, we talked about this a couple of videos back. The overall proportion is just P with a line above it, and it's just the sample counts divided by the sample total. So in this case, there were 120 females, 12 are left-handed. Of the 180 males, 24 were left-handed. So our focus here is on being left-handed. So the proportion of males who are left-handed is the same, at least that's what we're testing, the proportion of males that are left-handed. So we're going to count those left-handed from the females, count those left-handed from the males, add those up and divide by the total sample size. So about 12% of our, 12% of our 300 children are left-handed. Now, finding the expected frequencies, guys, I'm not going to get too much into this. This will make a lot more sense in the next video. It's a very simple calculation. It's just the row total times the column total divided by the sample size. And when you see that in action, it'll make it a lot clearer. I don't know if it'll make it clear or not, but it'll be easy to calculate the expected value. Plus, once we learn how to do StatCrunch, StatCrunch calculates the expected values for us, which is really cool. So guys, ultimately, and again, this is just kind of, this first video is just trying to introduce you to chi-square. At the end of this video, you're just going to be extremely dangerous if you go out and try to do a chi-square. But anyway, you can see that in each cell count for female and male, either being left or right-handed preference, we have an observed count and an expected cell count. So the chi-square statistic compares what we observed with what we would expect under a true null hypothesis. So in this case, the chi-square statistic, if you want to follow along with me here, go down to the very bottom row, and you can see that we're just summing up a bunch of stuff. We're taking the, in each cell count, we're taking the observed minus the expected squared divided by the expected, and we're doing that for each of the 4 cells here. And in this case, our test statistic turns out to be 0.7576. So guys, then we go to our decision rule, and I'm going to show you how to come up with your critical value. In this case, it's 3.841, which you can see in large red letters down at the bottom. And it works the same thing as the other distributions that we've found critical values before. So we compare the critical value of 3.841. We see that our test statistic of 0.7576 falls to the left of that in the do not reject region. So we conclude there's no evidence, or at least no sufficient evidence, that the two proportions are different. So we can extend this into more proportions. So we don't necessarily have to just compare proportions over 2 like we did with left-handed over males and females. Maybe we want to compare left-handed across some political parties, maybe Republican, Democrat, and other, in which case we would have more than 2 independent populations. So in that case, we would have that the proportion of Democrats who are left-handed equal the proportion of Republicans who are left-handed equal the proportion of moderates or other, I think I called it other, who are left-handed. And the alternative is just not all of the proportions are equal. So it reminds you a lot of the ANOVA case, except we're dealing with proportions instead of means. All right, so again, the chi-square statistic, the degrees of freedom, very important. It's always the number of rows minus 1 times the number of columns minus 1. So again, that will stick and more easily be tattooed to the brain when you see it in action. And computing the overall proportion is essentially the same. So guys, the great thing about, in my opinion at least, about hypothesis testing is once you get the fundamentals down, even in something new like this chi-square statistic, which I would bet that most of you haven't seen before, it's still the decision rule and comparing your p-value to your alpha, it's still the same. We just have to get a solid understanding of what our null and alternative hypotheses are. So guys, finally we get into a chi-square test of independence. This is where we have our a contingency table. And the null hypothesis is the two categorical variables are independent, meaning they're not related. There's no relationship between them. And the alternative, I think I said alternative, the null hypothesis is the two categorical variables are independent. And the alternative is the two are not, or are dependent, or they're not independent, which means there's a relationship between them. So guys, chi-square statistic is calculated the same. Then you'll see each, down at the very bottom, you'll see that the degrees of freedom, as I said earlier, the number of rows minus 1 times the number of columns minus 1. So if we have a 2 by 2 table, we have 2 rows, we have 2 columns, so R would be 2 and C would be 2, so we would have degrees of freedom 2 minus 1 times 2 minus 1, which of course is just 1. Expected cell count frequencies can be found by taking the row total times the column total divided by n. Again, we can do that manually, or we can have StatCrunch do it. And guys, decision rule is the same. So an example here that they ran through is they have class standing. And again, keep the eye on the prize here. All of our variables in chi-square are categorical. On the rows, we have class standing, classification, freshman, sophomore, junior, senior. And then they've categorized the number of meals per week as none, 10 per week, or 20 per week. So the hypothesis to be tested is the meal plan and class standing are independent. Someone may have a motivation to study this by thinking that, well, freshmen are maybe more likely to buy a meal plan because as you get to a sophomore, junior, senior, a lot of universities, many of those many of the juniors and seniors especially move off campus and get an apartment. Now, I found something interesting. University of Kentucky played center in basketball recently, and they were given. In fact, a good friend of mine graduated from center, and she told me that when she was there, you had to live on campus and you had to get the meal plan until you were a senior. I think she's 48 or something, 47. So it's been a while. I know she probably sounds ancient to you guys. All right, guys. Expected cell count frequencies again. Let's just do for the junior 20 per week. What they did is they took the row total, which is 30, the column total, which is 70, and multiplied those two together and divided by 200, and they got the expected cell count of 10.5. Now the chi-square statistic is going to add all those things up. Again, it's going to take each cell, it's going to take the observed minus the expected squared over the expected cell count. So we have 6 degrees of freedom, and guys, what we're going to see here is our critical value is 12.592. Our test statistic is 0.709. So there's insufficient evidence to conclude that meal plan and class standing are related. No relationship. All right, guys, in this chapter, well, you know what I did. We did chi-square test for comparing proportions and for contingency tables. If you're sitting here right now and you kind of feel like you're in a fog, it means you're normal. But I tell you, just I promise you, just give me the opportunity to teach it to you. Once we look at an example and see how these calculations are done in StatCrunch, you'll see. I think this will be some of the easiest stuff that we've done in some time. So, guys, take care.